Since ancient times, humanity has always yearned for a unified explanation for all phenomena in nature. We've had brilliant successes with Einstein's theory of relativity describing the universe on a large scale, and quantum mechanics explaining the microscopic world of particles. However, these two great pillars of modern physics deeply contradict each other when attempting to unify them. We need a theory of everything, a single framework that can explain all forces and particles in the universe. And today, we will delve into one of the most promising candidates, string theory. Could these tiny strings of energy be the ultimate answer to all the universe's mysteries? Welcome to SpaceTime's Universe Journey of Discovery, where we explore the deepest mysteries of the universe. In this video, we will explore string theory, the ultimate solution for the theory of everything. Don't forget to subscribe to the channel so you don't miss out on other exciting universe exploration videos. If you find the video interesting and useful, please like and share to support us. For centuries, physics has made remarkable progress, from Newton's law of gravity to Einstein's theory of relativity and quantum mechanics. Each theory has succeeded within its own domain, but none can encompass the entire picture of the universe. The contradiction between general relativity and quantum mechanics becomes particularly apparent when we try to describe extreme conditions, such as inside a black hole or at the moment of the Big Bang. This is when the need for a theory of everything becomes more urgent than ever, a framework that unifies all fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, along with all matter particles. In standard quantum mechanics, fundamental particles like electrons or photons are considered dimensionless points. This model has achieved astonishing successes in describing the microscopic world and particle interactions. However, when applying this point-particle concept to gravity, the equations become uncontrollable, leading to infinite and meaningless results. This is the biggest weakness of the point-particle model when attempting to unify gravity with other quantum forces. String theory emerged with a groundbreaking idea. Instead of point particles, the fundamental building blocks of the universe are incredibly tiny one-dimensional strings of energy. Imagine these strings vibrating like guitar strings. Different frequencies and modes of vibration of these strings will create different types of particles with different masses and charges. For example, one vibrational mode could produce an electron, another a photon, and most importantly, a special vibrational mode produces a graviton, the particle that mediates the gravitational force. This elegantly solves the problem of gravity. When strings interact, they don't just exchange point particles, they also transmit vibrational modes. The appearance of the graviton in the string's vibrational spectrum naturally incorporates gravity into the quantum framework. This immediately made string theory a promising candidate for the theory of everything, as it inherently includes gravity from the outset. One of the most surprising aspects of string theory is its requirement for extra spatial dimensions. In everyday life, we only experience three spatial dimensions: up, down, left, right, front, back, and one time dimension. However, string theory requires the universe to have at least 10 or even 11 spatial dimensions for its equations to be mathematically consistent. The question then arises, why don't we see or experience these dimensions?
The most common answer is the concept of compactification. These extra spatial dimensions are curled up into extremely tiny structures, only detectable at the subatomic level. Imagine an electrical wire. From a distance, it appears one-dimensional, but upon closer inspection, you see its two-dimensional surface curled up. Similarly, these extra dimensions might be too small for us to perceive, yet they profoundly influence how particles and forces interact at the microscopic level. The precise shape of these curled-up dimensions would determine the physical constants and types of particles we observe in our universe. Another pillar of string theory is supersymmetry. This is a theoretical symmetry that proposes every fundamental particle we know, fermion, has a supersymmetric partner called boson with a different spin and vice versa. For example, an electron, fermion, would have a supersymmetric partner called a selectron, boson, and a photon, boson, would have a partner called a photino, fermion. If supersymmetry is true, it would help solve some major problems in the standard model of particle physics, such as the hierarchy problem related to the mass of the Higgs boson. Supersymmetry also plays a crucial role in making string theory mathematically consistent, eliminating troublesome infinities. However, to date, experiments at large particle accelerators like the LHC have not found any direct evidence for these supersymmetric particles. This poses a major challenge because if supersymmetry doesn't exist at energies we can explore, then string theory needs an explanation for its absence or it must be modified. The world of string theory doesn't just have one, but 5 different string theories, all mathematically consistent. These include Type 1, Type 2a, Type 2b, and 2 heterotic theories, heterotic SO32 and heterotic E8 times E8. At first glance, having so many theories might seem contradictory to the goal of finding a single theory of everything. However, the emergence of M-theory promises to unify these 5 theories into a larger framework, which we will explore in more detail in the next video. One of the most challenging problems of string theory is the landscape problem. Given the enormous number of ways the extra spatial dimensions can be compactified, there could be up to 10 to the power of 500, a colossal number of possible universe configurations, each with different physical constants and types of particles. This makes it extremely difficult, almost impossible, to make specific predictions and verify them experimentally. How do we know our universe is one among trillions upon trillions of others in this landscape cultivator?
Some scientists propose that this could lead to a multiverse concept, where each different configuration corresponds to a separate universe. Our universe is simply one of those, where physical constants allow for life and galaxy formation to exist. This is a fascinating but also controversial idea, as it pushes the boundaries of verifiable science. String theory also offers profound insights into the nature of black holes, one of the most mysterious objects in the universe. Stephen Hawking showed that black holes have temperature and radiation, Hawking radiation, which implies they have entropy, a measure of disorder or the number of microscopic states. Conventional quantum mechanics struggles to explain the entropy of black holes. However, string theory has provided a way to count the microscopic states of black holes, and the results perfectly match the Bekenstein-Hawking entropy formula. This is a huge success, demonstrating string theory's ability to connect gravity and quantum mechanics at the most extreme limits. It offers hope that we are on the right track to better understand how the universe operates at its most fundamental level. Verifying string theory is an enormous challenge. The strings are predicted to be unimaginably small, approximately 10 to the minus 35 meters, the Planck length, billions of times smaller than a proton. To directly observe these structures, we would need a particle accelerator the size of a galaxy, which is beyond our current technological capabilities. Therefore, physicists must search for indirect ways to test this theory. Indirect verification methods could include searching for supersymmetric particles at the LHC, though unsuccessful so far, or looking for subtle effects of extraspatial dimensions in precise gravity experiments. Cosmological signatures from the early universe, such as primordial gravitational waves, could also provide important clues. However, the lack of direct experimental evidence is one of the biggest criticisms of string theory, keeping it more in the realm of theoretical mathematics than experimental physics.
Despite its immense challenges, string theory remains a vibrant and promising field of research. Its mathematical elegance, its potential to unify all fundamental forces, and the profound insights it offers into the nature of space-time and matter all make it an attractive candidate for a theory of everything. It represents humanity's ceaseless quest for the deepest understanding of the universe, a journey that Carl Sagan once described as unlimited exploration. This theory has been driving significant advancements in many areas of mathematics and physics, even if it hasn't yet been experimentally proven. It opens new doors for thinking about the universe, from the possibility of a multiverse to the strange structures of space-time. Whether it is the ultimate answer or not, string theory has certainly changed how we perceive what is possible in our physical universe. String theory has opened up a new horizon, showing the potential to unify forces that once seemed impossible to connect. But could the 5 string theories truly be just different facets of the same coin? And is there a grander framework, a foundation that genuinely unifies all physical theories we've ever known? In the next video, we will step into the mysterious and promising world of M-theory, a potential candidate to answer these questions. M-theory is not just a theory, it's a supertheory, a complex web connecting all variations of string theory and even more. Join us to discover if M-theory holds the key to the complete theory of everything, and what it brings to completely change our understanding of space-time, gravity, and the entire universe.